All right, let's get started because we have a packed session. So hello everyone, welcome to Science Extraction with the ngEHT. We have a great lineup of 5 different talks today. I just want to let people know, and the presenters know ahead of time, each talk will have 10 minutes with 2 minutes of questions, and I'll put out a warning at 9 minutes. I'll just say 1 minute left, just so you know, but you don't have to stop and tell me, okay, good, or anything, just to warn you so we stay on track. I want to encourage interactions and good questions at the end. So please, like during the talk, if you have questions, just put them in the Zoom chat, and then we can really get to them quickly. Try to get as many as possible, and the ones that aren't answered, you can either answer in the Zoom chat later. The presenters can answer there over the Slack, which should continue after the session is over too, the Slack channel. I also want to note that we have to, we're doing this thing where we're providing these high-level bullet points to the chairs of the discussion sections. So if you find anything particularly interesting or exciting or unexpected in the presentations, just make note of it in the Zoom chat, and I'll compile these and try to condense them down to 3 to give to the discussion chair. So it'd be great to get your help on that as well. All right, so let's get started. Our first talk is going to be from Freek. Freek, are you there?
Yes, I'm here.
Okay, Freek did his PhD at Radboud University, and now he's a postdoc at SAO. And he's going to be talking about SIMBA and applications. Oh, anything close? SIMBA and applications, synthetic data for next generation VLBI arrays. So take it away, Freek.
Okay, thanks, Katie. Yeah, so I'll be talking about synthetic data and give you some examples of what we can do with it. So when we generate the synthetic data, we want it to be as realistic as possible, as close to the real data as possible, because then we can make a direct comparison between the real and simulated data and extract the science that we want and develop algorithms for that. And apart from that, with synthetic data, we can also investigate the performance of VLBI arrays under different circumstances. So we can vary the site locations, the weather, antenna properties, and with that help optimizing the design of new VLBI arrays such as the ngEHT, but also optimize our observing strategies for existing arrays. And then we can also test different steps and algorithms in the data calibration. And we've also found it useful to educate students about the different concepts in VLBI. So the synthetic data generator that I've been developing together with Michael Janssen is SIMBA. And this is an end-to-end VLBI simulator that is simulating both the observation and the calibration. And we base everything as much as possible on first principles and physical models and parameters that are measured at the sites themselves. So this diagram, you can see the inputs that go into SIMBA, simulation. So we have all these properties of the antenna itself. Then we have an atmospheric model, which is an important component because the atmosphere really affects these high frequency VLBI observations. We simulate the pointing offsets of the antennas. And then when you put in the telescope location and an observation schedule, which can be a real one that has been observed or is planned to be observed, and then you can give it a source model, and SIMBA will then generate the raw synthetic data and then pass that through a calibration pipeline, RPCard developed by Michael. And then it will do a fringe fitting and amplitude calibration, and then you get a calibrated data set. And that you can then use, for example, to reconstruct images. So here you can see an example of a GRMHD model that we put in. And here we took the 8 telescopes of the 2017 configuration of the EHT. And we can see this is M87. So like in the real image, we see this asymmetric ring structure. And then when we add these 4 sites, 3 of those are hopefully also joining in the EHT campaign this year. We can see that the image gets sharper, and we see a hint of this extended jet structure. And this extended jet structure we may be able to image more deeply with a lot more stations, but the ngEHT. But here we've gone one step further and also simulated space field VLBI observations. So we've been developing this event horizon imager concept consisting of 2 or 3 satellites in circular medium Earth orbit at a slightly different radius. So as they orbit, they will slowly drift apart, and then you get this nice spiral-shaped, very dense UV coverage up to very long baselines. And if you go to a frequency of 690 gigahertz, you have a nominal resolution of about 4 microarc seconds. And then you can see here in this simulation that you then get an image reconstruction that is really much sharper than what we can do from the ground. But apart from looking images, we've also been doing some parameter estimation with the synthetic data using the grMHD models. So we generated this grMHD library for M87, depending on black hole spin, magnetic flux, electron temperature distribution, and each of these models have 100 different frames. So they vary in time. And then in the fitting framework that was developed for the 2019 publications of the EHT M87 results, each of these frames is scaled and rotated to optimally fit the EHT data. And the angular size that you then get determines in the end the mass of the black hole, if you know the distance. What we are now doing is using synthetic data as input for different arrays and see how things change when we improve the array. And we've been using this genetic algorithm GINA developed by Christian Fromm to do the optimization. So apart from using different arrays, we also simulated multi-epoch observations. And that is because, as I will show, our ability to extract these parameters is really limited a lot by the variability within these grMHD models. So in the top row here, you can see that for different frames of the same simulation, the emission can look quite different. But then, as shown here on the bottom row, when we average multiple frames of this simulation, we start, as we average more and more, we start to wash out this turbulent variable structure, and we are left with an image that is much more dominated by the lens photon ring, which also makes the fitting much easier. So here we can see that in some results. So here we took an input model and simulated observations of a frame of that input model and fit that to the other frames of that same input model. And if we, here we see the distribution that we get in the black hole mass when we do that. So when we go from blue to orange, from EHT 2017 to 2021, we can see some improvement, but we see a very big effect when we observe 10 frames and average the observations before we fit. And we get a much better constraint on the mass, and this improves even further when we employ this high frequency space field VLBI array. Then apart from the mass, we are also, of course, interested in all these other grMHD parameters. And to constrain these, we use this average image scoring selection procedure developed for the EHT, which tests if the input data, so in our case, the synthetic data, is consistent with coming from a realization of the variability within the model that you are fitting to. And here you see for each of these, for a particular input model for these VLBI arrays, for each spin, you see what fraction of the accepted models has this spin. And when you look at, for example, the red bars, which is an extension of the EHT 2021 with 6 stations, you can see that we already favor the true input spin of 0.5, and for example, this spin of 0.94 is ruled out, at least within this library. And then we get a large improvement when we go to space. And we see that only spin 0 and 0.5 models are accepted. Then here we see the width of the distribution of the masses of 40 different arrays. The blue points here correspond to the distributions that I showed a few slides back. And the orange points are the uncertainties in the masses, the mass measurement, when we consider the full library after this model selection by average image scoring. And we see some interesting trends here. So we see a large jump, for example, here and also here, when we go from 1 frame to 10 frames. So this indicates that this multi-epoch observations could be really, really useful. But we also see that despite the model selection, there's quite a large gap between the mass that we get when we fit to the full library versus to the input model only. So that is telling us that it may be important to constrain these GRMHD parameters independently, for example, with multi-wavelength observations. And then when we look at this point here, we see that with the high frequency EHI, we can get to a mass uncertainty, in this case of just 0.5%. And the 0.5% also happens to be approximately the uncertainty by which we know the mass of Sagittarius A star. So this will make GR tests very interesting. So here are some directions for the future. I won't go through them in a lot of detail, but we are continuously developing the SIMBA pipelines in various ways. And apart from the science extraction method that I've shown here, there are a lot of other things you can do. You can, for example, instead of doing this averaging, actually make use of the variability or do use a more specific metric to measure the mass, like a ring fit, and use machine learning to interpolate between the GRMHD parameters. And what we've not done so far is make use of the large-scale jet structure, because the field of view of our simulations was relatively small. But when we do that,
I forgot to give you 1 minute warning, so if you could wrap up fast, that'd be good.
Okay. Yeah. So we expect with an extension of the EHD, we can better use the large-scale jet for our parameter estimation. But despite all those developments that are still possible, we already see some interesting trends. And I think that things are looking optimistic for the future. That's it. Thanks.
Thank you. So clap. Okay, we have a number of questions, so I'm going to try to ask them in the order, but we only have 2 minutes. So any other questions we can put in the chat or Slack. So the first one I saw hand raised was Aditya.
Yeah, so I saw a rather concerning statement in one of the slides in which you said that EHT 2021 plus rules out the spin of 0.94. Is that an instrumentation problem? Is that a data analysis problem, simulation problem? Like what ruled out is a pretty bold statement. So I'm trying to understand the rationale behind that.
Yeah, sorry. So maybe I should have explained this in a bit more detail. So what we did here is we took a simulation, a geometry simulation of a spin of 0.5, and then simulated observations from that, and then see which of these models, when we fit the synthetic data, are still acceptable. And then we found that when we try to fit models with spin 0.94 to the data that was taken from a simulation with spin 0.5, that these models, all of these models, do not provide a good fit. So that's what I meant with. So
it's a simulation problem, basically.
It's limited by the library that we have.
Right. Okay. Thank you.
Great. So actually, we're at the 2 minutes now. So why don't the other questions I saw Hugh also had his hand up. Could we just answer them in the chat or Slack? move on to the next one. Thanks again, Frank.
Okay.
Our next talk is from Dom Pesci from the Center, Harvard Smithsonian Center for Astrophysics. And he'll be talking about a D-term modeling code called DMC for simultaneous calibration and full Stokes imaging of very long baseline interferometric data. So go ahead.
All right, thanks, Katie. Yeah, I assume you're able to see my screen and hear me, and I'm just going to proceed. Today I'm going to be giving a speedrun style overview of DMC, which is a Python-based code that I've developed for doing polarimetric imaging of VLBI data while simultaneously performing station-based gain and leakage calibration. DMC uses a Hamiltonian Monte Carlo sampling framework so that the end product is a set of samples from the joint posterior distribution of both the full Stokes image and a number of calibration quantities. I'll start just by very quickly reviewing the imaging problem that we're trying to tackle. As I think we're all aware, the complex visibilities that we measure, which fall on the left-hand side of this equation here, aren't the perfect Fourier quantities that we'd like them to be, because they've been corrupted by a variety of effects that are captured here using a Jones matrix denoted by J. The Jones matrix can in principle contain any station-based linear corrupting effects, but in practice, we tend to be most interested in calibrating out the complex gains and the polarization leakage terms. The underlying true visibilities, uncorrupted visibilities, are related to sums and differences of the Fourier transforms of the four Stokes images, the four Stokes structures in the sky. And here I'm just using a tilde to denote a Fourier transformed quantity. And then, of course, the Fourier transformed Stokes images are themselves related to the sky plane Stokes images by nothing more than a Fourier transformation. And so the polarimetric imaging problem is then just the project of determining the underlying Stokes images given the observed parallel and crosshand visibilities in a manner that accounts for all of the corrupting effects along the way. And this is the problem that DMC has been designed to solve. So DMC is a forward modeling software. It's analogous in many ways to EHT imaging and SMILey, these RML methods that see regular use within the EHT collaboration. The underlying image model is a square grid of pixels, with the intensity in every pixel being a model parameter. But of course, in each of these pixels, there's really 4 Stokes parameters worth of information. And in DMC, the Stokes quantities are parameterized using a spherical representation. This is also known as the Poincare sphere or the Stokes sphere. And in this diagram here, we can see the 3D space of Q, U, and V with the Stokes vector in red having a magnitude equal to this little p here, which is the polarization fraction. And then its orientation is determined by the azimuthal angle alpha and the polar angle beta. And this azimuthal angle is related to the EVPA, while the polar angle is related to the amount of circular polarization. This spherical parameterization is very convenient because it automatically enforces this physical inequality that the total polarized flux must not exceed the Stokes I flux at any location in the image. So we thus have 4 model parameters associated with every pixel, namely the set of alpha, beta, p, and I. And given these, we can translate the spherical representation back into the Stokes representation for the purposes of Fourier transforming, converting to parallel and cross invisibilities, and then applying corruptions, as I sort of breezed through in the previous slides. But of course, although DMC uses a forward modeling approach like the RML imaging methods, it's not otherwise operating in the same way as them. And for one, DMC explores the joint parameter space of polarized images and calibration quantities all at once, rather than in some sort of iterative process or in some linearized regime. And this here is just a super quick example of DMC performing a fit to some synthetic data. It's been compressed by a factor of more than 100,000 in time. And the point here is that just all of the relevant parameters are varying simultaneously. And so that at the end of it all, we have a solution for not just the image, but also for the station gains and leakage terms. Another somewhat minor way that DMC differs from the imaging methods that are in use so far is that it actually makes a point, somewhat pedantic point, of fitting only to complex visibilities, where the likelihood is pretty strictly Gaussian, even at arbitrarily low signal to noise ratios. But of course, the biggest selling point is probably the fact that DMC returns posterior samples rather than just a single maximum likelihood style image, which comes at the significant cost of computational expense, but which otherwise affords a number of advantages. Okay, so onto a couple of demonstrations of DMC in action. Here's a comparison between the input and recovered Stokes images for a DMC fit to a synthetic data set that was generated to have similar properties to the M87 EHT data, including all manner of station corruptions. And we can see here that the gross structure in the recovered Stokes images appears to be rather well recovered across the board, which is reassuring. But the model images also clearly are showing this sub-beam scale structure that isn't present in the original images. And so we can do the usual trick of convolving everything with some nominal beam, and things start to look a whole lot nicer when you do that. But of course, these images now, these smoothed images no longer represent something that actually fits the data. And it's natural to ask at what resolution level we can actually trust the DMC output, right? Because the original resolution images looked like they were full of all these artifacts, and you'd like to know how much you need to smooth the image before all you're seeing is believable structure. And the answer to that is actually that you can trust the DMC output at its native resolution, artifacts and all. And the reason is that DMC comes with a built-in measure of uncertainty in the form of the image posterior. So here I'm just going to focus in on one of those 4 Stokes images, the Stokes V image, because it's the noisiest one. And so I think it demonstrates this point most clearly. So I've gone back now to showing the unsmoothed image, and we can see that it looks pretty rough. But if we take a look at the uncertainty in every pixel, defined here as the standard deviation of the image posterior, we see that it also has quite a lot of structure. It's not a uniform uncertainty across the image. And by differencing the model and input images and then normalizing by this uncertainty, we can see that the residual map is pretty much just noise. And so what this is saying is that the input source structure is fully recovered, even at this choppy native resolution, so long as you understand, you interpret these features or any recovered structure as being significant only at the level determined by the uncertainty. And it's rather natural to cast this degree of uncertainty in the form of something like a signal to noise map shown here. And nowhere in this map does any single pixel ever exceed a signal to noise of 3. So in that sense, we would say that this fit did not recover any statistically significant Stokes V structure from the synthetic data set. But the gross model structure is rather suggestive side by side with the input. And as an example of a fun thing that you can do with the DMC output, here I've just divided the image up into 2 regions and computed the integrated signal to noise in both of them. The selection of the regions here is admittedly been informed by the known input structure, but we can see that after doing it, we actually do recover a somewhat marginal detection of positive Stokes V in the upper left section of this image. And we can play even more sophisticated games with the DMC output to obtain posterior distributions for quantities that were never model parameters at all. Here I'm showing the input and recovered polarized images on the left, and on the right are posterior distributions for the coefficients of a couple of terms in this specific azimuthal decomposition of the polarization structure that was developed by Daniel Palumbo, George Wong, and Ben Prather. And the vertical lines in each of these histogram plots show the coefficient values computed from the input images. And the histograms themselves show the distribution of such values as computed using the posterior samples from DMC. And we can see that the distributions are consistent with the input values, indicating that DMC has not only correctly recovered the input polarization structure, but that it is also capable of describing exactly how well it has done so. And lest we forget, the DMC is also solving for the calibration quantities at the same time as it solves for the image structure. Here are the leakage posteriors shown in these contours for all stations compared against their truth values shown as the red and blue crosshairs. So this really just provides yet another check that DMC seems to be doing the right thing. Here's now a demonstration from the DMC paper of an application to real data. In this case, a 43 gigahertz observation of OJ287 from the Boston University Blazar group. And we can see some really nice consistency here between the polarized structure obtained using both clean and DMC when both images are convolved with the same restoring beam. I'd just like to thank Svetlana Jorstad and Alan Marsher for providing both their polarimetric image reconstructions as well as their pre-leakage calibrated data set for the purposes of this calibration or this comparison.
1 minute done.
Thank you, Katie. So here are the leakage posteriors that DMC recovers for each of the VLBA stations. And here I've overplotted the leakage solutions from LPCal, courtesy again of Svetlana and Alan. The VLBA observations were carried out using 4 IFs, and the original LPCal analysis solved for leakages in each IF separately, while with the DMC, I used a band average version of the dataset. And we can see here that by and large, the DMC leakage values really seem to represent something like the mean of those derived from LPCal, which is again, very reassuring. And before closing out here, I just want to note that DMC is still very much being developed. with a number of improvements having been implemented even since I submitted the paper, and more are planned for the near future. So with that, I'll leave up my summary slide and end the talk. Thanks.
Thanks, Dom. Awesome work. Awesome. Great presentation. We have a number of questions. The first one I saw came in from Kazu. So Kazu, do you want to ask your question?
Yeah, this is just a minor question. So how do you handle the pi ambiguity and in the polarizations angle in the in your HMC step?
Yes, that's a great question. So this spherical representation, right? The polarization angle is here, this alpha parameter, right? And the way I actually do this is that this alpha parameter is a real spherical, polar coordinate, and I sample it. I sample it in a periodic distribution. So I sample it in uniform periodic prior. So it doesn't view itself as being multimodal.
I see. Thanks.
Yep.
Great. Next question I saw is Matt Lister.
All right, there, you done mute. So Dom, your input model, and you showed your movie. Did you start out with a uniform, looks like a square prior there, on the top right? Yeah.
Yeah. So for the purposes of this demonstration, I just started with a uniform one. In general, DMC, this is for illustrative purposes. In general, DMC can start from any sample of the prior distribution on the image space, which I actually have as a default this Dirichlet prior, this constrained sum prior, so that you can independently set priors on the total flux as well as on the image distribution. So it's the sort of default is that it is uniform in the image. The prior is uniform on the flux in every pixel, but it's uniform subject to this total flux constraint, right? Subject total to the constraint that all of the pixels must sum to some total value, so that you can place a prior on that total flux value. So this is an example of a sample from such a distribution, but it's a very atypical one. Most times it'll seem a little noisier, kind of like what the sorts of things you saw in my second to last slide. These sorts of things, typically what an image might look like.
Yeah, it's just I'm curious to see how it handles cases where the a priori amplitude scaling is way off for multiple antennas, which is certainly the case of the LBA at 43 gigahertz.
Yeah, I think that would be a gain prior problem. That would be something where if you really have reason to believe that your antenna a priori calibration is way off and your gain priors didn't manifest that belief, then yeah, you would have a skewed reconstruction somehow. There is the option within DMC to set your gain prior. So you could set it if you think your gain is not centered on 1, your gain amplitude for some station is like 2 or 3 or something, you can set that.
And just one follow-up. So normally these observations are interleaved. So and the D terms aren't changing that much. So could you do this in multiple sources at once?
Yeah, right now DMC doesn't do multi-source fitting at once. I've hacked together a couple of things and done that internally, but I don't have any systematic thing in there right now for doing multi-source fitting. That'd be a good item for future development for sure.
Okay,
great.
Thanks.
Thank you. Sorry, Andrew and Saurabh, we have to move on, but Andrew, maybe you can ask your question in the chat. Okay, moving on to Daniel Palumbo, who's from the Center of Astrophysics, Harvard Smithsonian. And he's going to talk about forward modeling short-period black hole parameters and emissivity distribution.
Hi there, folks. I hope you can hear me. I've been having weird issues today. Can people hear me? Hello?
Yes.
Awesome, wonderful. Okay, great. So yeah, hi there. I need to clear out 10 Zoom screens here. Yeah, so I'm here to talk about, as Kitty said, forward modeling short shield black hole parameters and emissivity distributions, which I will hopefully convince you to call blimaging by the end of the talk. This is an ongoing project in collaboration with Dominic Chang, Zachary Gellis, Michael Johnson, Dom Pesci, and Paul Tita, all of whom are at the conference. So to begin with, a bit of philosophy. Why do we make images? We make images to answer non-parametric questions like, what does M87 look like? We try to make minimal assumptions about the data and essentially only have priors on things like smoothness or essentially smoothness broadly construed in various ways, all these different regularizers. But ultimately, we think that this is a decent representation of what's actually hitting our telescope. But we also make models. Why do we do them? Well, it is not merely by convention that we display these VLBI images with little scale bars on them. We care about how big or how thick the objects we look at are. And in the particular example of the angular size, we are interested in statistically rigorous estimates of parameters like the angular size. What I'm showing you here is the one of the Ring-Gauss models from paper 6, where it's rather manifest from this diagram that we are making a very specific mathematical prediction for what one of these crescents will look like on the sky, and we're interested in the statistical distribution of those parameters. However, going from these geometric parameters to something physical that we is really what we care about, like the mass, in the case of the ngEHT work, requires a calibration to GRMHT. What this means is that the mass that we get out of imaging or these geometric model fits is inextricably tied to, in essence, blurred GRMHT simulation snapshots, which is a perfectly reasonable thing to do and a way to harmonize across many different methods, and it's wonderful. But for many members of our community for whom the methodological limitations of the GRMHT and the ngEHT library are somewhat unsettling, this puts the mass estimate into question. And so in the new analysis method that I'm going to briefly outline for you today, we're going to keep a few goals in mind in light of this philosophical meditation. We'd like parameters, or excuse me, posteriors on black hole parameters like mass, spin, inclination, position angle, all of these things, while avoiding calibration to simulations. And part of avoiding that calibration requires maintaining structural agnosticism in the same spirit as imaging. We want to allow complex emission morphology and to forward model that in parallel with forward modeling of the actual black hole parameters themselves. And all of this is possible if you assume GR and essentially solve the same image or non-parametric model fitting problem for the emissivities rather than intensities on the sky. We're essentially making minimal assumptions besides essentially optical thinness and solving the same problems in parallel with forward modeling the black hole mass. And so before we get into the details, I want to tell you why bother doing this very hard problem. Why put yourself through this? So emission structure is interesting. This plot on the left is from, I think, figure 4 in ngEHT paper 5. It came up at the end of George Wong's talk this morning. Even if we aren't forward modeling at the level of magnetic fields and electron number densities, just figuring out what part of the accretion flow is glowing can be deeply informative about the mechanisms at play. Whereas on the right, I have this figure from Gralla, Holtz, and Wald in 2019, which calls into question the inference done by the ngEHT in assigning a mass to a particular ring diameter, essentially from the argument that certain distributions of emitters and their velocities can obfuscate the true black hole mass just by virtue of putting light not where you expect it. And for both of these reasons, it's useful to have complex, arbitrary geometries for your emitters in a forward modeling paradigm so that you can access it for science extraction and also marginalize over it for the purposes of measuring more sort of abstract things like the black hole mass or inclination, what have you. And so with that in mind, here is Boyer-Lindquist imaging, or blimaging. Everything I'm going to show you is in Schwarzschild and also in a plane, just to keep it simple and easy to visualize and easy to implement selfishly. So on the left here, this is a little cubic grid that I've stretched over my black hole. And I have a grid in radius and azimuthal coordinate. And at every vertex in this grid, you can imagine we have a little infinitesimal spherical emitter in the same spirit as DMC's grid pixels. So we're solving the same problem just in a polar grid at the black hole. And we're going to follow 4 of these just for pedagogy and our sanity. So in red, orange, green, and blue on the left, keep your eye on those colors. We're going to follow them as they make their way to the observer on the sky. So we've picked some inclination. And so this gives us this characteristic bent plane image. And we can see where these blixels land in their direct images, which are n equals 0. And we can go as high n as we want. So we can go to n equals 1, n equals 2, and they'll fall closer and closer to this critical curve, which I'm showing in black. I'll point out that this is still scale free in terms of mass. So we're parallelly fitting the mass here in our forward model, and scaling the mass will just scale all of these in or out. The position angle will just rotate them around. And ultimately, once everything is baked in, you get the interferometric response, where any one of these blixels will just produce some little ringy thing from the n equals 0 and n equals 1 lensed appearance of these delta functions beating against each other, but together they produce the familiar sort of fall off that we expect. And so these three images together are essentially the entire forward model for going from emissivities in a plane around a black hole to an interferometric response for comparison to data. I will point out, however, that generating this forward model is actually quite computationally expensive because, in general, for Kerr, in particular, you need to do root finding and numerical integration to actually generate these screen positions. And so using approximations to get analytic screen positions makes this much easier and much faster. If it's analytic, it's auto-differentiable, which means you can write this up in PyMC3 and have it going pretty quickly, which is what we've done. And in particular, this is using the Bela-Borodov approximation, which gives you strikingly accurate Schwarzschild geodesics, particularly at low inclinations. Dominic Chang, who's at the conference, is working on an extension to spin. So stay tuned for that, keep an eye out. It's very exciting. But yeah, for now, our model is just going to leave out Kerr. So we're just in Schwarzschild, forward modeling mass, inclination, the position angle, a static and axisymmetric fluid velocity, and the two-dimensional blimage of blixels. And we can include visibilities from however many sub-images we want. In the future, 3 dimensions, blocks of bloxels, we'll figure out the name later. Time variability and time lags from these blixels will be of great interest, as we've heard from Shahar and others. And of course, magnetic fields and polarization, and ultimately spin will be the holy grail. So I realize I'm near time here, so I want to end with a sort of unit test for this approach. I'm seeing many people raise hands. I'm excited to get to this, but imagine, if you will, that we have a black hole that's a little under half as massive as M87, so around 3 giga solar masses, and we put a just little ring of 8 blobs at a radius of 9m. Then when we actually look at this completely face on and blur it to say 10 microarc seconds, which is conservative for the ngEHT perhaps, but ambitious for the EHT, this doesn't really have any indication that you have this interior photon ring, which is the clear signature of its mass. It just is a minor alteration to the brightness floor in the central depression. And keep in mind that without this photon ring, this problem is completely scale-free in terms of mass. So if you were to try and fit this with 3DMC and without any sensitivity to the photon ring, there's no distinction between a large mass black hole with lit up interior radii and a small mass black hole with lit up exterior radii. And so if we actually break this degeneracy, it means 1 minute, great. It means we have some access to this lensing feature, which breaks this degeneracy. And so if you plug this in with incredibly unrealistic observing standards, just as, again, a unit test, which you should not overinterpret, and take a random image from your posterior, these, it turns out you have an incredibly sharp posterior on mass, and you get essentially exactly what you're looking at. So do not overinterpret this. Do not walk away from here thinking, well, we have the photon ring. We should expect M87 photon rings tomorrow. But I want people to not short sell a ground-based array when it comes to accessing the photon ring. I think it is well within reach in certain super resolving model fitting experiments. So I will leave it here. I realize I'm probably coming up on 10. This blimaging is under development. Hopefully we'll be on the archive soon. It's enabled by these beautiful analytical approximations, which more are coming. There's a lot of very exciting work being done by some local collaborators on the screen. And I think this is a way for the ngEHT to get around some of the fundamental problems with existing EHT measurements. Thank you.
Thank you, Daniel. Very nice work and presentation. Okay, we have lots of questions. I think I saw Andrew's hand shoot up first.
I'm going to try to unmaximize my screen so I can look at the chat.
Yeah, thanks, Daniel. Great talk. I think I asked you the same question before, but I'm still unsatisfied. Why do you use these? I mean, I understand you use these very artificial seeming pixels in space. And I think, why don't you just use some sort of extended emission description? I think you said that's because you want there to be some analytic description for the the emission on the observer screen. I don't see why that's really necessary when you just have a gridded model and still have everything be fully differentiable. Am I missing something?
Sorry, so you're saying use a fully, like some smooth analytic description for the emissivity?
I'm saying you could do a lot of different things with the emissivity. But yeah, like for example, you could have you could have a series of rings in the equatorial plane, or you could have a power law in radius and some breakdown into azimuthal modes in azimuth, right?
Sure, I guess you can do really any description you want, right? For the emission near the black hole. I guess what I like about essentially pixelating it or rasterizing it is that you can allow for non-axisymmetric structure or just weird structures that you would not expect from a steady state GRMHT, right? But there's nothing too prescriptive about this exact parameterization. Do whatever works.
Sure. Okay. I think that makes sense. I think last time you explained it to me in that like you wanted this was the only type solution that would give you an analytic type image, and I just.
Oh, sorry. So there's I guess there's two problems here. One is in the model prescription where you're sampling an intensity, then the problem is simple, right? Because you're essentially following a single ray. But if you have to worry about the lensed appearance of something, then the Fourier transform no longer becomes simple. So if I had a Gaussian, right, in the equatorial plane of the black hole, then its lensed appearance is non-Gaussian, and its Fourier transform is complicated. So it's easier to take the limit of many delta functions, all of which have simple Fourier transforms, than something more complicated.
Sure, I just think it might be more natural to do it with a rasterized image plane, but yeah,
right. But then you're solving the problem backwards, right? If you're rasterizing the sky.
No, because you can differentiate it either way, I think.
I think this is a good conversation. Can we move it to the chat or Slack because we're running late?
Okay, sorry. Yeah, good point.
Okay, thank you, Daniel. Sorry for the questions we didn't get to as well, but
yeah, I'll chat with people else.
Yeah, chat in Slack or Zoom. Let's move on to Joshua from University of Illinois, Urbana-Champaign, who is talking about feature extraction on synthetic black holes with neural networks. Take it away.
Yeah, can you hear me? And can you see my screen?
Yep.
Yeah, cool. My voice is pretty low, so just let me know at any time. So hi, everyone, I'm Joshua. So today I'm going to speed run through one of the projects I've been working on. It's feature extraction on synthetic black hole images with neural networks. And this has been done in collaboration mostly with member George, Ben, and Charles at UIUC. So a little bit of introduce of myself since I'm new to a lot of people. I've been working on Charles gave me on machine learning application for ngEHT, mostly on image domain, but recently we've also started exploring parameter extraction on visibility domains. So the story begins with, we know like with this black hole image, what kind of science can we do with this image? And in my personal opinion, I think spin is one of the most interesting parameter because it's actually changed the geometry around the black holes. And the other question we have in mind is that there are many good talks that talks about how we can constrain spin using a physical model. But the other thought of thinking is that can we do it in a data-driven ways? So by saying data-driven way, which means that you have some theory and you use this theory to create some of the models and try to compare how closely your models is with your real observational data. And fortunately, at our group, we have lots of these simulations. And on the left-hand side is the full resolution of our simulation, which is done using iHarm3D and IPOL, which is the GRMHT and GRRT codes. And on the right-hand side is the blurred version of our simulations that mimic how the current resulting power of the ngEHT was seized. And I think most of you have seen this movie many times, so I'm not going to jump into details. But the idea is that with lots of these simulations, we can actually take snapshot of these image to generate lots of image data. And coming back to this question of spin, and one of the things I found really challenging is to look at one of these images and directly guess what spin is, because one of the reasons is that the in-class variation between spin is actually pretty huge compared to across different spin values. So I found it really hard to just directly look at one image and tell what the spin value is. And to make it even worse, I think what George and people found is that in our simulation, there could be possible degeneracies that, for example, like right here, there are two black hole image I select in the red box, that they actually contain different spin value, but they look very similar at certain point during the evolutions. To make it even worse, when you have blurring effect, they basically look very similar or even the same. So if you're using something like a chi-square fitting on it, and estimating spin probably wasn't working very well at this moment. So at that time, I think we decided to look into other alternative options. So one of the things that are in recently really exciting is machine learning, in particular deep learning, which means that you are using machine learning with deep neural networks. And deep learning have been performing really well in computer vision tasks. Like in the past 10 years, there are many benchmarks that shows that deep neural network can achieve almost superhuman performance in many computer vision tasks. So for the question we have right here is that given lots of these images and their label, the label right here means, for example, like spin value, can we estimate a parameter of our interest? And lots of people know that neural networks are good at something we call classification. They are good at classifying cats and dogs. And in our case, there are some natural cases where we want to do classification, for example, like MAD or SAME models. But for other parameters, they're actually continuous distributed value within certain range. For example, like spin and inclination angle. And you can actually do something we call regression, which is directly output the value you want at the last layer of the neural networks. So due to the time, I'm going to focus on the high resolutions of our simulation in this talks. And obviously, I want to give a huge credit to, there's a really nice paper called Deep Horizon. I think it's led by Jeffrey Van der Kook et al., which use similar neural network techniques and try to classify spin. And this is sort of like an extension of their work. So in our work, I think we use ResNet 18, which is more deeper, and I personally really like this convolutional neural network. And in our work, we modify a last layer of a neural network so that it can output the parameter of interest, including spin. And we use a mean square loss error so that it can directly output the value of the spins. And in our model, we include both MAD and SAME as our training set, and we validate on another 100,000 of images. So one thing to, after the training has been done, one thing to really test our neural network is to see how well it performs on a blind data set, which I personally don't know what the answer is before George really unblinded for me. So at the top column is a blind data set A. So in principle, if our model works really well, then they should look like 5 delta functions right here. And we found that it did indeed perform pretty well. Then we decided to get it more challenging by changing some of the plasma physics we have in our simulation and throw it to our neural network to see how well it performs. And that is indeed why we set up blind data B. And it actually turns out that indeed there are more scattering in blind data set B when we do the estimation. However, the neural network still performs relatively well. So I think it's in some sense able to generalize it. But because due to the computational cost, we only have 5 spin value in our simulation. So our ultimate task is to see how well it can perform on other spin value, because it's very unlikely that the real data is going to have these 5 exact spin values right here. So we tested on spin equals to 0.75 and 0.25. And our neural network model shows that even though the distributions have to influence by its prior, but the mean value of these predictions actually pretty close to the ground truth. So which makes us really exciting and really think that the neural network really learned something that is important in these synthetic data sets. And so the next question we have is that, well, obviously this works pretty well. So how can we see what the neural network actually learns instead of just treating it like a black box or a big function approximator? And this is one of the cartoons that I really like. If some of you have experience with machine learning, usually when it doesn't work, just tune something and then suddenly works, and we don't really know why. But as a physicist, that's not very satisfying. So we decided to look into something called the feature maps of these neural networks, which is the intermediate output of our neural networks. So one thing, I think most of you are really familiar with convolutions. So one thing right here is that these are some of the internal structure within the neural networks. And one thing that is different from usual convolution is that these convolution kernels are actually being learned during the training process. And there's usually some downsample effect right here. So in our neural network, there are basically 5 natural places for us to output these feature maps. So one thing we found really useful is that is at basic block and basic block 1 and basic block 2, which is a unit within ResNet. And the reason why this is working well instead of these two is that usually at the last few layers there, because of the downsample, it's really hard to recognize what's going on. And at the first layer, it's pretty similar to your original input. But we found that at basic block 1 and basic block 2, their feature maps contain a lot of you can still recognize the ring-like structure, but there's a lot of features being generated right here that worth for study. And so by looking into some of these feature map, one thing we did is that to compare the trained ResNet with something called untrained ResNet. And by saying untrained, it's actually a ResNet that have been seeing cats and dog or natural objects, but they have never seen a black hole before, or synthetic black hole before. So by comparing these two, we can sort of think of what kind of unique features are right there in our synthetic black hole image that could be related to spin. And one of the features we found is that there's actually a lot of these spiral arm pattern or low surface brightness patterns showing up, which I select in the green box. And there are actually 64 of these feature maps within the ResNet basic block 1. So there's actually a lot of them. I show this because I just want to show you that I really think this is one of the important features for how neural networks are able to estimate spin with such a high accuracies.
1 minute.
And yep, sure. So and why we call this low surface brightness feature is that when you plot the image in log scale, you can actually see there's a lot of patterns showing up right here. And we think that neural network are really found these patterns contain lots of information about spin, which is really exciting for us. And due to the time, I'm not going to talk about this, but I would just go directly into summary. So I hope that I convinced you a neural network could provide a really interesting tool for us to study these synthetic black hole image. And they are also good at feature extraction, using as a tool for feature extractions. And one of the exciting things that we've been thinking about is to build an end-to-end tool so that neural network can directly be analyzed on these radio interferometry feasibilities. And obviously, more feature work would be needed for further study. So I think I'll stop here and take questions. Thank you.
Thank you, Joshua. Okay, great talk. And I really like seeing the feature maps and stuff too. So I think our first question was from Michael Janssen. Michael?
Yes, very interesting stuff. I was wondering why.
Michael, it's very hard to hear you. You just sound very staticky.
Oh, okay. Stan?
Miguel, your mic is heavily distorted. If you have another way to get audio in, that'd be good, or just type.
I can read his question out loud. Why have you chosen ResNet 18? Have you also tried deeper networks like ResNet 50?
Right, so that's a very good question. So we actually try lots of different versions of these neural network, and at some point we found ResNet 18 is sort of like a neural network that have skip connection that performs really well. And however, they are sort of saturated when you start to increase more layers. So ResNet 18 have similar performance with ResNet 101, I would say. So I think ResNet 18 is pretty good.
Okay, great. And then one quick last question is it on GitHub?
Yes, but unfortunately, it's I think it's still private right now, but we're thinking about making it open source someday. Yeah.
Okay, thanks. Martin, sorry, I asked your question for you so we could do it fast.
Yeah.
All right, thank you, Joshua. Moving on to the last talk of the session is from Saurabh from University of Delhi, and he's going to be talking about Gallifrey, a geometric model and parameter estimation framework for black hole images using Bayesian techniques. Saurabh, are you there?
Yeah, thanks for the, just a second, I'll just share my screen quickly. Okay, I hope my screen is visible.
Well, it looks like, yeah, let's see it in presenter mode.
Okay,
Yep.
So thanks, Katie, for the introduction. My name is Saurabh, and I recently completed my undergrad from University of Delhi. So this talk is actually a continuation of a talk given by Saurabh Nambaliwar on first parallel session on theory-independent test of GR using VLBI and black hole images. So basically, I'll be presenting here a library that we constructed for the analysis of the data that we have simulated and constructed for our particular work for geometric modeling and parameter estimation. So what exactly is Gallifrey? So I'll just giving a brief details about what exactly is the scope of this particular library and what are the things that we can do with this whole stuff. So firstly, it's a modeling tool. We can model any radiant interferometric source, be it a general relativistic image or be a geometric model. We can use both of these different images to basically model out a particular source. Secondly, you can extract some basic parameters such as diameter, width, or total flux intensity from the images. We use Bayesian formalism for the basic parameter extraction, and this whole thing is actually written in Python. So due to the time constraint, you might think that this whole thing might not have that much of scope. But as we say that using time-law science, basically this whole thing might look small from the outside, but actually is bigger from the inside. So this is a basic workflow for the testing of this whole library, that how we can test out using some simulated data sets. So first we try to simulate some data sets. We choose a test model. Let's say, for example, we chose some particular geometric model. Using some fiducial set of parameters, we construct some synthetic VLBI. So for constructing those synthetic VLBI data sets, we use ngEHT imaging library. Then we choose some particular model for parameter estimation, choose an appropriate likelihood, then construct the priors with some initial guesses, and then simply run the MCMC sampler over those particular models. And then we try to extract whatever the uncertainties and the parameters that we have recovered, we get using the posterior distributions. Now, this whole step looks very easy and also looks very time consuming. So basically we use a parallelization for running our own, this whole code. We have been using small cluster at the University of Tübingen for running our sample codes. So this is an example of the visibility modeling. We actually use some simple geometric models at first to actually approximate a black hole accretion image. As you can see here, we first use a simple crescent image, which is nothing more than a subtraction of two disks, filled disks. And this is how we try to simulate it. And then we simply convolve it with some Gaussian kernel as to see how we can actually see it in some radio, in radio astronomy, how we can see that. So this is an example how we do it. It's quite simple. We just simply set up the parameters of the particular model that we need to simulate. We choose a particular model. So we actually use this excess ring Gauss model explained in Beckenwich 2016. So we use this excess ring Gauss model, create the image object, then we draw this simply the intensity map in 2D domain. And then we simply convolve it with some interstellar scattering kernel. For example, here we have used for Sagittarius A star, and this image looks very similar to that of black hole accretion image. So that's the power of some these geometric models, which they actually try to approximate those accretion or those radiation flow images that we receive from VLBI. Now we take a further step towards the image reconstruction. We try to test out the library in some extreme cases. We first try to simulate some image using the library. Then we use ngEHT imaging library to basically reconstruct those, reconstruct the image as per what ngEHT will see using this 2017 array configuration. And this is the reconstructed image that we have found. Now we try, first we try to simulate some data sets and try to fit the models to that particular set of model that we want to choose. Now we actually fitted some fitted the models to these M87 results that we that ngEHT found in 2017. So here are the plots for the visibility amplitudes over the baseline length. So as you see that we first choose a model. We took excess ring model, which is simply subtraction of two disks and with some nonlinear brightness across its disk structure and how it will fit to MET7 data results. So the results seemed quite very similar to those published in ngEHT 2017, and as per the expectations, we were able to find some those parameters very similar to those published in 2017. So for the analysis here, we actually chose 500 walkers and 1,000 samples, which obviously wasn't that enough to actually get us a very, very good result, but at least as per what was expected, we were able to explore the whole parameter space. The model parameters that we thought initially, we were able to recover that as well, and we're getting some proper contours as well. So for plotting this library, we just took a step further for giving a reference to this Doctor Who series. So this is the TARDIS module that we have used to construct this particular posterior distribution plots, which we name it as triangular posterior distribution module. So what exactly are the capabilities of our Gallifrey? So we have currently included these total of 8 models in our the whole library. So these 8 are basically just geometric models. As you can see, we have included some simple models and also these generalized crescent models, as you might have seen in the ngEHT papers as well. These are the number of parameters on which these models are dependent on. And for detailed information about the parameters, you can simply follow the reference papers as well. So we have actually included both the image domain images and also the visibility domain analytic results, as well as to increase the to reduce the computation time and get our results as fast as possible. So in the first release, we have included only the first 6 models. In the second release, we are going to use these parameterizations of these excess ring models, which we have named as ngEHT excess ring, and ngEHT excess ring goes in the second release, which will be done pretty much soon. And also in the second release, we'll be trying to have the ray tracing capability as well, that will not just be simulating this geometric models. We'll also be using some simple accretion models as well. For example, a static black hole surrounded by some spherical accretion, and how we can actually try to recover the parameters from that particular accretion model. So the code can be found on this particular link, Gallifrey. The second release is going to be soon, and feel free to pull some requests on this particular library, and also feel free to create an issue as to have some good yeah. So I guess that's it. Thank you so much. I'll be happy to take up any questions.
Thank you, Saurabh. Any questions from the audience? Okay, I have a question. What would you like? What is the next big item that you would like to add to this model, basically?
Okay, so basically, I think this is where my extra slides are going to be handy. So for the second release, we are thinking that we are going to do this nested sampling for the MCMC and adding some more models apart from what we have already included. For example, if you want to model some jets, or some model some extended sources as we get from radiant difframetry, how we can do that. So we're trying to add that, and also looking into a different domain, which is space VLBI. So if that's possible to add to this, add that particular part in our library, that would be wonderful.
Great. It's so good to have other kinds of software packages that we can build off of as well.
Yeah,
so,
definitely.
Yeah. So thank you all. I think we're going to end here. We're already cutting into the break time. So I think thank you for a wonderful session. Thank you to our 5 great speakers. If there are any remaining questions, please put them in the Slack channel, and we'll reconvene in the main session, I guess, in 10 minutes. I'm putting together a list of a few bullets, but if you have suggestions, let me know. So talk to you later. Bye.
Thank you, Katie.